Alright, so we've talked about the add point function, the add prim function, and the add vertex function. And so now the question is, can we kind of combine all these things together in a way that might be useful in a production environment? So I will give an example where I use these three functions to to take care of a problem. Um, Sorry, I was drinking some coffee. So the project had I was doing some visual effects for a figure skater. It was like a figure skating animation, and we needed it to kind of go in like a perfect spiral. Well, actually, it wasn't indicated that it needed to be a perfect spiral, but I wanted it to be a perfect spiral, and I was going to use the spiral to kind of be the path that I would use to kind of animate along the figure skater, and then I could also use the path generate um, to generate sparks and like little snow flakes and stuff like that. Um, so um, so what's kind of interesting about we've learned about this idea about making our own geometry, and if your particular program doesn't have a spiral generator, you might be a little bit out of luck. But because we can make our own custom geometry in Houdini, and what I mean is we can kind of when you make a sphere like in Maya or something like that, um, basically there's some formulas behind the scene that are generating that primitive, right? So the idea is that as long as we know the equations for generating shapes, we should be able to kind of use our vex functions that we can build geometry with to create those shapes and basically make new primitives, which is really cool. Um, so I did some research on like how spirals work, kind of mathematically, and there's kind of this famous logarithmic spiral that's generally kind of used in many different things. It kind of appears in nature all over the place, but it's called kind of the golden spiral. Um, and the great thing about today's world is that you don't need to understand exactly where these equations come from, just how to kind of use them. So um, I I just looked up the equations. So the first one they give me is in polar form. Polar graphing is pretty useful for graphing certain types of things, especially certain curved kind of shapes. But the problem is uh, it's maybe not as helpful for us in Houdini because generally we're talking about x, y, and z space. So I'm actually going to use these parametric equations here. So what parametric equations are is uh, rather than having it rather than having a function rather than having an equation explicitly defined as uh, y in terms of x. So for example, um, if I were to to do maybe you know you've seen something like maybe y equals x squared, right? Which is a parabola. So in this case, my y position is determined by my x. They're totally dependent of each other, right? You can't change the x without changing the y. So the cool thing about a parametric equation is we're actually dividing up the x and y positions or components, I guess. If we're kind of thinking about things in terms of vectors, we're taking the x channel and the y channel and we're kind of dividing them up so they each have their own equation. So if we look at this here, how do we get the x position of our spiral? So any point on here, right? How do we get that? Well, we basically do r times cosine of theta. And how do we get the y position of any point on our spiral? Well, that's just r times sine theta. So that's cool. We can definitely use that. And then there's another kind of important thing here where cosine and sine are just mathematical functions, and then theta is going to be our variable that's going to change. So to create our spiral, we might plug in 0 for theta, and then maybe a little bit further than that. Like we could plug in 1, and then 2, and then 3, and then 4. And as we kind of plot those points, you'll get the kind of natural spiral. But um, but R is interesting because R is based on kind of another equation where you have a times e to the b theta. So e is a number that's similar to pi, or it just kind of occurs in nature. Um, and so similar to pi, where the number pi was showing up a lot in mathematics, especially when the ancient Greeks were kind of studying this stuff. So rather than kind of keep saying 3.1459 over and over and over again, they just kind of gave it a special name, which was pi. So the same thing happened to e. E is sometimes called the natural number because it shows up in nature a lot. Um, for example, a lot of times um, different like population growth models are usually modeled by something like y equals e to the x, where maybe a population starts growing slowly, but as soon as it starts growing, it starts to really kind of take off. So e is another kind of really useful number to know if you're interested in kind of um, modeling real world types of simulations and stuff. E is a number that shows up a lot in the real world, so that one and pi I think are just two numbers it's good to kind of get used to. So theta is still just theta, right? Theta is the number that's going to be changing. So like I said, maybe we'll start at 0, then we'll plug in 1, and then 2, and then 3, and then so on, so on. So theta is going to keep changing, but a and b are actually arbitrary constants. What that means, if you're ever trying to kind of figure out what equations mean, an arbitrary constant is basically a number that you can pick a number for it, and it'll be that number kind of throughout your calculation. So, for example, if we choose a to be 1 and b to be 2, then a will be 1 and b will be 2 for the entire kind of calculation. So that's kind of a lot, but the key is to kind of really break it down. So I'm going to do a little, let's see. I'm going to do a little notepad here and kind of make some notes. So let's see. So we have, so to figure out where our points are going to go, each point is going to need an x position, right? And then each point is going to need a y position. And then we need a constant. So our constants are going to be a and b. So we'll keep that in mind. And then r is going to be based on a and b. And then theta is going to be our variable that changes. So I'll say theta is the variable that changes. Okay. So then we can say, okay, x position is r times cosine of theta, and then the y position is equal to r times sine of theta, and then r is basically a. I'll just do lowercase. Let's see, I should probably make these lowercase. So r is going to be a times e raised to b times theta. Okay, so I've kind of got my I've kind of organized my thinking a little bit. I've decided, okay, so a and b, I'm gonna make channels for these. So basically, so I'll put maybe next to it, so like I'll maybe put some notes like make channels for these so that the user can change these parameters, right? So A and B will have channels. Um, let's see. Um, R is based on A and B, so we'll make that calculation in the code. Theta is the variable that changes, so that's one thing to keep in mind. And then let's see. Yeah, I think this is kind of enough to go on. So I'll kind of bring this back and reference it a bit, but I'm kind of moving this over to my second monitor for now. But just so you know, like, this can be kind of helpful to kind of organize your thoughts when you're kind of tackling something pretty mathematical like this. And then one thing that I'll do also is I will use some sort of graphing utility to kind of check my math to make sure that I'm actually getting the thing that I want. So Desmos is a great graphing calculator that's free, it's online. And I just did a basic parametric equation here where this equation right here is for the x value, and then this equation right here is for the y value. So I just put in some numbers for a and b, right? I made a 0.1 and b 0.1. T is kind of my stand-in for theta. And then e, remember, e is not a variable, it's just a number, right? So if you look at all of this, I know it looks kind of complicated, but really the only thing that's changing is t, okay? And then right here, I can kind of dictate which t values to plug in. So basically this says, hey, start at 0 and then stop at 6 pi. I could stop like wherever I want. Like I could stop at 2 pi, but that's maybe not as illustrative of the point. So you see like the more t values I plug in, kind of the bigger and bigger my spiral becomes. But this looks cool. Like this is the shape that I'm trying to make. So, you know, my equations, I can be confident that my equations at least are correct. So now it's up to me to code them correctly in Vex. But if I don't get a spiral, it's not the math that's wrong, it's me that's wrong. So this kind of gives me the confidence to kind of go forward knowing that if I can nail these equations, I will get my spiral. So let's jump into Houdini and get to it. So one thing that's kind of that we didn't really go over in previous lessons is in previous lessons we used a point wrangle node to kind of add points to geometry. But remember that we kind of ran into a problem because of the parallelism of Vex. Every single point that was in our geometry was kind of executing that code, right? So this is kind of an example where that's going to be a huge problem for us, because if I have geometry with like 100 points, each one of those points is going to try to make a spiral, right, when it tries to execute the code. So one kind of useful thing you can do, the makers of Houdini side effects, they're really smart and they kind of foresaw this problem. So this run over thing here is pretty interesting. Most of the time we leave it on points, but there's this option for run over detail only once. And what this does is it kind of fixes the problem where earlier we were maybe having just point 0 run it, or we were saying if your point number is 0, run the code. This kind of does the same thing, because it basically it will look at the code and it will just run through it once. It'll just execute the code once. So this is a really kind of handy way, especially if you're using Vex to kind of generate geometry, rather than manipulate existing geometry that you have. This detail only once option is really useful because it kind of removes the problem of like stacking a bunch of different extra points that you don't want. So let's think about this here. So one thing that that I kind of am kind of thinking about right away is that I want this spiral to kind of be on the XZ plane. Because remember in Houdini 3D space, if I kind of go, if I set the view to perspective, um, right, like this is, you know, this is the x-axis, the depth is the z-axis, and then up and down is the y-axis. So if I use x and y to make my spiral, it's going to be kind of like, um, it's going to be facing, it's not going to be on the plane that I want it to be. So if you look at this kind of this little widget down here, when my mouse, maybe, yeah, let me move this around so you can see better. Yeah. So if you see this here, um, you can see that, looking at it this way, this is the XY plane, but I actually want it to kind of lay on the ground. So if I kind of rotate my camera, you can see, with this little widget here, this is actually the XZ plane. And if I set the view to the bottom viewport, then this kind of looks like how we would expect a graph to look, right? Where here's the x-axis, and then here's what in traditional math we would kind of think of as the y-axis. But this is a little confusing, but I promise it's not a big deal. Instead of using the y-axis, we're going to use the z-axis, right? So if I look at my equations, anywhere where I was using y position, let's change it to z position. So that's pretty simple, right? It's not that big of a deal. So now let's go ahead and get started. Enough yammering. So, looking at our notes, we know we're going to need an x position, and we know we're going to need a z position. So I'll go ahead and just initialize those up top here. So I'll go x pos and z pos. Just initializing those variables. I'm not going to populate them yet because those variables are going to change each time, right? Every single point on the spiral is going to have a different x position and z position. But I just want to kind of initialize those up here. Now, another thing we have to kind of keep in mind is when you're kind of using a graphing calculator, and I'm saying I want to go between 0 and 8 pi, it's kind of infinitely accurate in the sense that it's plugging in 0 and then a number a little bit bigger than 0 and then a number a little bit bigger than that, and so on and so on. And that gives us like that perfectly smooth kind of graph. Well, we don't have that luxury because we're not going to plug in an infinite number of points. That's just not going to work for us. So we have to kind of think about our total points that we want to use to graph. And it might be useful to give our whoever is working on this control over the number of points, so they can maybe add more points if they feel like they need to. So the number of points, let's think about that. Number of points, are we ever going to have 5.5 points? Are we ever going to have 6 2/3 points? No, we'll always have like an integer number of points, right? So we can go ahead and initialize that. We can say int for integer, and we can say total points. And let's go ahead and make that a channel, an integer channel, right? So ch for channel, I for integer. And let's go ahead and call that total points. And what that's going to do is, if I hit this little button here, that will give us an option to dictate the number of total points. I'm just going to do 100. I feel like 100 is a good number for us. So we've given the user control over the total number of points to use. So now, looking at our equations here, we've got a few things that we need to kind of plan ahead for. One thing is, we know that our equation is going to use this number e. Now, I don't know if Vex has like a built-in value for e, but sometimes you want to kind of define your own value so that it's not taking up too much memory. So what I mean by that is, if I look at the number for e, this is the number for E, right? It goes on forever, 2.7182812, right? So on, so on, so on. For our purposes, we don't need this much accuracy. We probably just need like the first maybe 5 decimal places. So, uh, what I'm gonna do is I'm gonna make a float value. I'm gonna make a float variable called E, and I'm gonna go ahead and set that to 2.7. Let's see, what is E here? 2.71828. Okay, so 2.71828. 2.71828. That's plenty accurate for me. And then conversely, we're also going to need a value for pi. So pi is 3.1459. Um, we'll do one more decimal place. So I'm just going to look up the value of pi real quickly. So 3.14159.2. Okay. So now I've got some values for E and pi. So now when I use E and pi in my equations, my code will know what numbers to kind of use for that. So let's see. So that looks good. Now, we want to kind of plan ahead and take into account that, again, with our graphing calculator, um, you know, you plug in 0 for t and you get this point, right? And then you plug in a number that's just a little bit bigger, and then you get this point, and then so on and so on and so on, right? But for our purposes, we need to kind of define a step size, meaning that we'll start at 0, but we need to figure out. We'll start at 0 and we'll pick an end point. Maybe we'll do 8 pi or something like that, or maybe we'll do 6 pi. But we'll have our start point and we'll have our end point. But we need to figure out a step size, meaning that between 0, our starting point, and 6 pi, our end point, how much you're going to go up by each time. So let me give like an easier example to think about. Let's say our starting point is 0 and our end point is 10. So we could count like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? But to get even more accurate, we could do 0, 1 half, 1, 1 and a half, 2, 2 and a half, 3, and so on and so on, right? So the step size is going to be equal. It's going to be equal. Basically, I'm dividing up this space between 0 and 6 pi equally. So how can we do that? What would be a good idea? Well, I think a good solution to this is to basically take so we know it's going to be a float, so we'll say float step size, and we'll take our destination, which we know we want. I think we said we were going to do 8 pi, right? So we'll do 8 pi, and we'll go ahead and divide it by the total points. And this is going to work out great because the more points you have, the more accurate your spiral is going to be, because that step size is going to be like a finer and finer distance, basically. So basically, by tying the step size to the destination, which is we want to start at 0 and end at 8 pi, and then dividing it by the total points, that kind of gives us some control over the step size. So one thing because I did this example before I started recording, one thing that is going to be kind of important to realize here is that 8 pi is going to be in radians, and by default, Houdini's going to it's going to work with degrees. So we can just put a radians function in front of this expression here. Well, it's not really an expression, it's just a number, 8 times pi, and it will convert this value to radians for us. So that's just something we just kind of have to do. That's a little bit of a gotcha. It's kind of hard to get around that. You kind of just have to know that in math there's two different ways to express your step size around a circle. You could either think about it in degrees, right? 0 to 360 is one rotation, or you can think about it in radians, right? 0 to 2 pi is another full rotation. So sorry, this is getting pretty mathy, but there's just kind of no way really around it. It's just kind of how you build things in the world, right? Everything's pretty much modeled off of equations, even things that don't look like they are. So now we have our step size, and now we can think about how we want to. Well, let's look at our notes. So what do we have and what are we missing? So I'll bring this over here. So we've initialized our x position, we've initialized our z position. Oh, constants a and b. We need to make channels for these. Okay, cool. Yeah, we can do that. So we'll go float a is equal to channel float a, and then float b equals channel float b. Awesome. So that's giving our user some control over this spiral. I'll just initialize to some values of 0.1. Alright, so we did that. So cool, we've got our constants. Okay, so now we can kind of get into kind of the calculations. So we know that we want to basically create a bunch of different points. So what tools do we have to kind of do things a bunch of times? I think the one that kind of comes to mind is a for loop, right? A for loop is a great way to kind of to repeat things a bunch of times. So alright, so we'll do for, and we'll do int I equals 0. Go ahead, start at 0. We will stop when I is less than the total points, and we will add 1 each time. Alright, right, because we want to start at 0 and we want to basically step through for each point that we've decided we want. So if we have 100 points, we want it to loop 100 times. So starting at 0 and then ending when less than 100, it'll stop at 99 basically, right? So let's see. So for each point, we know that it has this value r, and it's going to be equal to a times e raised to the b times theta. Okay, so we have our a, we have our b, we have our e, but we haven't defined r yet. So let's go ahead and do that. So we'll go float r is equal to, so we know it's going to be a times, and then now this is kind of where it's tricky. You would think you could go like e raised to the b times theta, but the way you do like raising to powers in Vex is use a function. Actually, use the pow function. So what the pow function does, stands for power, is actually says right here, raises the first argument to the power of the second. So we want to raise e to the b times theta. Right, so that's going to go ahead and give us what we want. So now I just realized we don't have theta defined here. So we know we want to start at 0, so we could do float theta equals 0. And then we want theta to increase by the step size each time. So what we can do is we can kind of plan ahead that at the end of the loop we'll go ahead and do theta plus equals step size, right? because basically what's going to happen is we'll start at 0, we'll run through the loop, and then we'll add this step size to our theta. And then the next time we go around, theta will be slightly bigger. And then, the next time through the loop, same sort of thing. So, so that's going to take care of that for us, which is nice. So we have our r, so let's see here. So we have our r, we have our theta, that's the variable that changes, so we've kind of controlled that. So now I think we're actually ready to calculate our x and z position. So x position is r times cosine theta. Okay, that's standard enough for us. So we'll do x position equals r times cosine theta. And again, the reason why I don't need to write float x pos is because I went ahead and I initialized it up here, right? So float x pos. So down here where it says x pos, it knows that that's going to be a float. And so for our z position, we want that to be r times the sine of theta. Oops, semicolon, not colon. Okay, so now we need to add a point. So we know how to do that. We go, and we're going to want to, just to kind of plan ahead, we're going to want to be able to kind of refer to this point later on in the code. So I'm just going to go ahead and initialize it as an integer. Remember, I could just go add point and then just go right into it. But if I want to refer to that point later in the code, the best thing to do is to give it a variable. And the point is always going to be, at the point, the add point function will always return an integer. So that's why I'm initializing it as an integer. So we'll do add point. We want to add it to geometry stream 0. And now where do we want to add it? Now that's kind of interesting. So let's just call it new position maybe for now. And now we kind of realize, like, ooh, we don't have a vector. We don't have a position vector yet, right? So let's actually make one. So we'll go vector new position, and we will set that. We'll use the set function to set the vector, and we're going to do, we want the x position to go in the x channel. We actually want to populate the y channel with 0, because remember, we want it to be flat on the xz plane. So all of our points will have a y channel position of 0, and then our z pos variable can go in for our z channel here. So basically what we've done is we've created a position vector that contains the x position that we've calculated right here, 0 for the y, and then the z position that we've calculated here goes right here. And so now that we have that position vector, when we add a point, we can go ahead and refer to that position vector, and that should work. So let's actually see what we get here. So not exactly what we thought, huh? So let's see here. What can we do? Maybe to 1 and 1. Maybe to 1 and 1. Maybe to 1 and 1. Oh, let's see. Let's maybe add some more points. So we are getting some points, but they're moving super slowly. They don't seem to be kind of changing the way we would expect them to. So I think the problem may be, so if we do, let's do f at theta equals theta. You know what? Because it's running as a detail, I can't do my normal trick where I kind of attach it as a attribute to look at. So let's see what's going on here. So if we look, let's go back to 100 points. So if we look at our geometry spreadsheet to kind of do some diagnostics here, we have 0 to 99. So it is making 100 points. So that's good. So we are generating some points. Let's see here. Theta equals 0. Step size is radians. 8 pi divided by. Let's try. I think maybe I might need to multiply this by I. Yeah. So what happened there was well, let's see here. If I do, I'm gonna change this. Do some experimenting here. So if I, okay, what if I actually don't do the radians here? Okay, so that actually, so interesting. So if I change this to like 8 pi, okay. So I think it kind of depends on your setup. You may have to kind of, you may not get it right the first time around. Basically, is what I'm trying to say. But I thought maybe I had to change this to radians, but looks like we're actually okay here. So as you can see, we have our spiral generated, which is pretty darn cool. And if I change these values, you can see we have some control over this. So what A appears to do is to kind of make it, you know, bigger or smaller, and what B does is it kind of changes how tight the spiral is. So, you know, you could get like the exact shape that you want. So this is really awesome. So we've basically generated like a totally new primitive. Basically, we could bundle this as a Houdini digital asset or an OTL and share it with the rest of our team. And now anytime anyone needs to make a spiral, we could be like, oh, we're going to use Andrew's spiral generator. So this kind of gets into kind of the technical, you know, what would be like maybe considered like a TD position, where you're kind of building tools for like other artists to use. So, all right, great. So we've got our points. So now, so we've made use of the add point function, but what about what about we want to make this a line maybe? So we could definitely do that. So one thing we could do is we could kind of use the trick that we did earlier, where we initialize a polyline as a new primitive. We just initialize it with no points, and then every time we create a new point, we'll go ahead and add it as a vertex to the polyline. So remember that a primitive is going to, well, if you create a primitive, it's going to return an integer. So if you want to refer to it later in your code, you want to kind of initialize that as an integer. So we'll do integer, and we'll do spiral line, and we'll do add prim. We want to add it to geometry stream 0. What type of primitive do we want to add? We want to add a polyline. Now here's where normally we would, you know, maybe do like start at point 0 and connect to point 100 or something like that. But in this case, we're going to do the trick where we add the vertices kind of as we go. So we just need an empty container for those vertices. So that's why we create a polyline. So we've got our polyline. It's called spiral line. So now, before we increase the theta, right after we make the point, we can do add vertex. We want to add to geometry stream 0. We want to add which primitive do we want to add the vertex to? Well, that's going to be spiral line. And then which point do you want to add as a vertex? Well, remember why we initialized it as int pt, so that we could refer to it later if we wanted to? Well, we want to refer to it, so we'll do pt here. And now what you'll see is we actually have a primitive uh, that is a line that connects all of those. Um, so pretty cool stuff. I think I get really excited about this stuff because I think it really kind of if you can kind of if you can start to do this sort of thing, then you are basically almost unlimited about the kinds of things that you can make, right? If you can understand the math behind creating a shape, then you can make your own shape generator. You're not reliant on what shapes the software ships with, basically. Because I know, like, in 3ds Max, they do have a spiral generator, but in Maya, at least the last time I checked, they don't. So I kind of hate being like beholden to like what the developers thought was going to be a useful shape or not. I want to be able to create the shapes that I want to create. So using Vex to kind of create these types of tools, I think is a really powerful use, and um, hopefully that will inspire you to dig in and learn some more Houdini. Anyway, best of luck creating. Hope this was a fun example and showed how we can use the add point, add prim, and add vertex functions to create our own geometry. And uh, if you want to try an example like this, maybe what I would try to do is maybe do a simpler shape, like see if you can maybe build like just a circle. Now I know there's a circle generator in every app, and so there's never going to be a time where you need to make a circle yourself. But it's just a good like exercise to do to see if you could do it. And then from there you can kind of try more and more complex shapes.